Greetings, everyone. We just did a whole bunch of one-dimensional conservation of momentum problems. All the things that we've done so far have been all in one line. Collisions like that, something like that. Now we're going to complicate it by having collisions in 2 dimensions, where they can go up like that. So this is very traditional kinds of physics problems. We're going to start slow with an example about a car crash at an intersection. Everything from this video series is going to be from the set of slides called 114_momentum 02. This is the second set of momentum slides, which will be primarily covering 2-dimensional collisions. Remember how we said that the change in momentum is equal to 0, and we always have to remember to include that it's a vector by denoting its direction? Well, that's still true. Now we can take this and break it up into x and y. Whenever you have a vector, any vector in the universe, you can always break it up into its components. And here we can break this momentum vector up into its x component and its y component. If the change in the total momentum is 0, then the change in the momentum in the x direction has to be 0, and the change in the momentum in the y direction also has to be 0. Let's take a look at the example that's listed on slide 3 of the slideshow that we're in, Momentum 02. This example says that there's a 1,500 kilogram car traveling east at 25 meters per second, and it hits a truck with a mass of 2,500 kilograms traveling north at 20 meters per second. So we should probably draw that out. Here is our car with a mass of 1,500 kilograms traveling east, and it hits a truck, mass 2,500 kilograms traveling north. The car was traveling at 25 meters per second, and the truck was traveling at 20 meters per second. We can also have that here. We've got our truck, we've got our car. They're going to smash into each other. How many momentum equations will this be broken into, and how many objects per equation? The question is going to be, what direction do they travel off at together after the collision? They're going to slam together, and kind of drift off together after they slam into each other. We first have to figure out how many momentum equations to break this into. Well, the really easy way to figure this out is to just ask yourself, how many directions are we looking at? Well, we're definitely looking at 2 directions, an x direction and a y direction, therefore we're going to need to break it up into 2 different equations. And then the next question is, how many objects do we have per equation? Well, we've got 2 objects, so we're probably going to have 2 objects per equation. Let's start writing this stuff down. Delta px is equal to 0. I'm going to look at this one first. P initial x is going to be the initial momentum in the x direction for the car plus the initial momentum in the x for the truck. Notice what's happening here. Suddenly I've got more and more subscripts to deal with. We're going to have the same thing here. Momentum initial in y is the momentum initial y car plus momentum initial y truck, and we should also be looking for final momenta, so this is going to have a second equation. Momentum final x is equal to momentum final x car plus momentum final x truck, and this one will also have a second equation. Momentum final y is equal to momentum final y car plus momentum final y truck. You can probably see right now these kinds of questions can explode out exponentially with the number of terms and the number of subscripts that we're going to look at. Don't be intimidated by that. Just take it one step at a time. It's always going to be, okay, change in momentum in x is equal to 0. Well, therefore, momentum initial x is equal to momentum final x. I can just take my x equation and my y equation and plug those in there. Let's do that. Momentum initial x car plus momentum initial x truck is equal to momentum final x car plus momentum final x truck. Okay, does the car have any initial momentum in the x direction? Well, it's going off like that, so I'm going to say yes. It's got some of that. Does the truck have any momentum initially in the x direction? Well, the truck was going off like that. I'm going to guess probably not, because it looks like that was just going in the y direction. So that ends up being 0. We can replace these with mv. This is going to be mass car velocity initial x car is equal to mass car velocity final x car plus mass truck velocity final x truck. Looking at this, well, the final velocity in x of the car and the final velocity of x in the truck, the question says that they crunch together. They crunch together, so they have attached themselves to each other. That means that the final velocity for the car and the truck will be the same in the x, and it'll also be the same in the y. But the x value will be different from the y value, of course. So we can say, to continue this off, we can say mass car velocity initial x car is equal to mass car velocity final x plus mass truck velocity final x. Same final velocity because they've crunched together. We can plug in the values that we know. 1500 times velocity initial x car, 25, is equal to mass of the car, 1500, velocity final x, plus mass of the truck, 2500, velocity final x. Oh, well, actually, we've just got one equation and one unknown here. So we can solve this. Not too bad. 1500 times 25 is 37,500, and that's equal to, what's that plus that? You can figure that out, 4,000. V final x, divide that by 4,000, and we get that V final x is 9.375 meters per second. We have done half the problem. We've done all this, and that ends up being just half the problem right there. Let's finish off this problem by looking at what's happening in the y direction. Previously we said that delta py is equal to 0, therefore p initial y is equal to p final y. P initial y is going to be the momentum initial car y plus momentum initial truck y. That's going to equal momentum final car y plus momentum final truck y. We can then replace those with the MVs. Mass car velocity initial car y plus mass truck velocity initial truck y is equal to mass car velocity final car y plus mass truck velocity final truck y. Okay, is there any initial velocity for the car in the x direction? Yes, but in the y direction there's not. In the y direction there's no initial velocity for the car. So that ends up being 0. The final velocity of the car in the y direction should equal the final velocity of the truck in the y direction. So we can plug in numbers, keeping that in mind. Mass of the truck, 2,500. Velocity of the truck, 20 meters per second, is equal to mass of the car, 1,500 kilograms, times velocity final in the y, plus 2,500, velocity final y. Therefore, 25 times 20, 2,500 times 20, that is equal to 50,000. 50,000 is equal to 4,000 velocity final y. We can divide that by 4,000 and get 12.5 meters per second. Velocity final y is 12.5 meters per second. Well, does that give us the whole everything? Does that actually solve this problem? We had before that velocity final x was 9.375 meters per second. Now we have velocity final y as well. We should probably convert that into a more readable format. The next slide asks us to find the final velocity, magnitude, and direction of the two vehicles immediately after the collision. Well, we've done this plenty. We can find v final magnitude by taking the square root of v final x squared plus v final y squared, and we can find theta by inverse tangent of v final y over v final x. And it's just a matter of plugging that into our calculator. Square root 9.375 squared plus 12.5 squared looks like v final magnitude is going to be 15.625 meters per second, or we can just say 15.6 meters per second. And what direction is that in? Well, theta is going to be, okay, remember, we probably want it in degrees, so make sure that you know what units you're in. And we can find the inverse tangent of the y, which is 12.5, divided by the x, which is 9.375. And we find that theta is 53.13 degrees. Let's just draw that out, see what that looks like. We always measure from the plus x-axis towards the plus y-axis going in the counterclockwise direction. Looks like something like that. 53.1 degrees at 15.6 meters per second. Does that make sense? We've got a car going a little bit faster and a truck which is a little bit heavier. Sure, that probably makes good sense, that direction and that speed. It's going to be going a little bit slower. We're thinking about right the moment after the collision, so it's still going to have a bunch of speed the moment after the collision, but just a little bit less total magnitude of the velocity, and the angle will be somewhere between the positive y-axis and the positive x-axis.